All right, we start here today with the common collector configuration. Now, as you can see here, this is for NPN, this is for PNP. We have the transistor. Now look at the peculiar way in which it is wired up. Okay, of course, I am not showing here the external resistors like what we did for the last configurations, but just to clarify that the collector, this is your collector, this is the base, and this is the emitter. So collector is common to both input as well as the output. That is the reason why it is called as a common collector configuration. Don't forget the concept of the two-port network, and then things will be in line. Similarly, we have here for the PNP device. Look at the polarities of these voltages. Okay, so what we expect here is that it is easier to talk about in terms of NPN. Look at the various important features here. This is the place where you apply the input. And what is that? It is between base and emitter. Okay. Whereas where you take the output across the emitter and ground. So this is basically the common collector configuration. Okay. All the other things remain exactly the same, except for that there is no resistor here. So we don't have RC, but we have the RE. Okay, and that is what is very, very important. Okay, we'll see about the various different issues now. Let us start with the current relations in common collector. So we already have the relation better switch to one node. That is a much better. Okay. All right. So current relations in common collector configuration. Let us start with IE. This is always going to be there, which is IB plus IC. Okay. So right now we are not interested in IC because IC is not the output current. If you go back and see, the output current here in this case is IE. So input current is IB and the output current is IE and not IC. Okay. So I'll just get rid of this IC. So I can write IE, which is equal to alpha times IE, which I am substituting here.
Sir, your writing is not visible.
Writing is not visible?
No, sir.
I've already shared the screen.
Yes, sir, visible.
One net is this one note is visible to all of you?
Yes, sir.
Maybe this guy is having his own problems here. Okay. So I can write IC as alpha times IE plus ICBO. We have this. We already know this equation. So then IE happens to be IB plus alpha. Now we're talking about DC here. So alpha DC into IE plus ICBO. I can write this as 1 minus alpha DC into IE which is equal to IB. Just a jugglery of the terms. Nothing great here. So IE happens to be 1 over 1 minus alpha DC into IB plus 1 over 1 minus alpha DC into ICBO. But we already know what is beta DC. We have already defined the term beta DC. So beta DC is equal to alpha DC divided by 1 minus alpha DC. These basic equations you always should remember. So I can have 1 plus beta DC is equal to 1 by 1 minus alpha DC. This equation can be easily be derived, basic mathematics. Now we can substitute this 1 over 1 minus alpha DC in this equation and I get IE is equal to 1 plus beta DC into IB plus 1 plus beta DC into ICBO. This is the equation that I get for IE. Again, we can ignore this term because it is very, very small, as all of you know that. So finally what I get is IE, that is the emitter current, is 1 plus beta DC into IB. Okay? Or simply IE divided by IB is equal to 1 plus beta DC. Do you see any resemblance of this equation with the with the equation for the ratio of IC over IB in common collector, a common emitter? Is there any resemblance? What is the relationship between IC and IB in common emitter? It is equal to beta DC if you go back and see. So this is nearly the same. Since beta DC is most of the times, in fact every time, beta DC is way too much greater than 1, I can write this equation as IE divided by IB is nothing but beta DC. So I have a similar kind of current gain. I have a similar kind of current gain as in case of the common emitter. This is a very important thing. So I can say current gains in common emitter and common collector configurations are nearly same. That is our conclusion. Okay. Now let us talk about the RI, the input impedance and the output impedance in common collector configuration. If you go back and see the biasing mechanism, you will see that the junction at input. So what is the junction at input? What is the junction at input? It is the collector base junction. Okay. Okay. I should write it so that you will not get confused with common base. Okay. So it is a collector base junction. Okay. Now you'll see that this collector base junction is actually reverse biased. You'll ask me how. For that, again, I have to go back to the presentation. Okay, here the collector base junction. You see here collector base junction. So this is N. Sorry, this is N. This is P, and this is N. Okay. So P, where is the P? Which is, I mean, what is the polarity at P? What is the polarity at P? It is negative. What is the polarity at N? It is positive. So what can you say about this junction? Whether it is forward bias or reverse bias? Yes, guys. Please respond. I'm waiting for your answer. Guys,
Reverse bias.
what are the characteristics of a reverse bias junction? We have already seen that.
Current is carried through minority charge areas.
Yeah, that is all right. But what about the value of the current over there?
Microamperes.
Yes, it means that whatever
Small
may be
current.
the input voltage, the current is going to be very, very
Small.
small. So if the current is going to be very small and if voltage is going to be large, even if I apply larger voltage, that is nothing but your input impedance. So delta VCB, which is the input, divided by the current IB. So what can I say about this factor here, this ratio here? This is in microamperes. This is in volts. So what can you say about RI? Whether it is high, low?
Low,
So
sir.
it will be higher
Very
because
high.
value current will be low.
Got it?
Yes.
So I can say that the input impedance or the input resistance of common collector is very, very high. Look at this, it is in microamperes, this is in volts, so naturally I'll be getting this in mega ohms. Okay? All right. In a similar way,
Yes, sir.
what is the output junction? So junction at output. What is the junction at output? It is the emitter base junction. Okay? And what is emitter base junction? Always the transistor has to be in active region. So emitter base junction is always forward bias. And we know that for forward bias, the resistance is going to be, now this is going to be the output resistance. Why? Because this is going to be a ratio of delta VEB to delta IE. All right. And now what about this? What can you say about this? Forward bias junction. Current is large. For a small change in the voltage,
Very low.
larger change. So what about the ratio? It is very
So it
low.
will
Low, sir.
So what conclusion can we draw? That is, for common collector configuration, the input impedance is very high. For common collector configuration, output resistance is very low. This is a very, very interesting feature. Okay, and we are going to use this particular thing for some other reasons later on. This forms a very interesting configuration. Okay, then let us talk about the voltage and the current gains. So as we know, in common collector configuration, base voltage input is kept always greater than the emitter voltage output. Why is that so? Just let me switch back to the presentation. I have not yet discovered a way of doing this fast. Look here. I am supposed to apply voltage here, and I am supposed to get input voltage here, output voltage here. As we know that this base emitter junction always has to be forward bias. Okay, so naturally this side or the base has to be higher than the emitter voltage. So base VB has to be greater than VE by at least 0.7 volts that we know now. Okay, so if I apply, let us say if I apply 2 volts at the input, what will be here? What will be the output? Remember, this is base emitter junction VBE, which is having a typical drop of 0.7 volts. So what will be this voltage? If you consider this loop now, what will be this voltage? Okay, let me calculate it for you. Call this VE. We already have this, and we have this loop over here. So what do we have? VBE. Yes.
1.3 volts.
1.3 volts. Okay. I hope you have understood this. But should I explain it properly?
Yes, sir.
So should I go into the details of how
Yes,
do I?
sir.
Yes or no?
Yes, sir.
Okay, very good, very good. I always appreciate the questions. Okay, VB. Let us call this voltage as VB. Okay, minus VBE, minus VBE, minus VE is equal to 0. How do I get this equation? I'll simply apply KVL in this input side of the loop. Got it? So
Yes.
what I get as VE is nothing but VB minus VBE. And VB, we all know that it is 0.7 volts. So this was 2 volts, this was 0.7. So as somebody rightly said, the answer is 1.3 volts. Okay. So this is your input, this is your output. So what is the current gain? What is the voltage gain? How do you define the voltage gain? Output voltage by input voltage. Output voltage is 1.3 volts and input voltage is 2 volts. So what is the gain that you are getting? It is less than 1.
0.65.
It is less than 1. This is 1.3 over 2, so it is less than 1. So what can I say about the voltage gain in common collector configuration? In common collector configuration, the voltage gain is always less than 1. In common collector configuration, the voltage gain is always less than 1. Let me switch back to our So what can I say about voltage gain here? For common collector, voltage gain AV is always less than 1. This is one very important thing. What about the current gain? We already have seen the current gain. This is the current gain. In fact, the exact value is this. So the current gain is 1 plus beta DC. We have already seen this. So this all says everything about the common collector configuration. We have seen the input impedance, we have seen the output impedance, we have seen the voltage gain, and we have seen the current gain. Remember that always in an amplifier, the major characteristics or major parameters that you have to think about is always the input impedance. Now I'll call generic input impedance as Zi, output impedance Zo, current gain, voltage gain AV, and current gain AI. This is always true for any amplifier circuit. Okay, so we have already seen the current relations in common collector. What about the input characteristics? And you'll see a very weird kind of characteristics. You see a very weird kind of characteristics here. Okay, so let us talk about this. So this characteristic is a graph of, see, it is input characteristics. So what we have as the input, it is IB versus VBC. That is the characteristics. Now we already have VCE equal to VCB minus VBE. If you look at this, you will be able to understand. Okay? Or we can say VCB is equal to VCE plus VBC. So when collector base junction is reverse biased and emitter base junction is forward biased, VBE is or remains around 0.7 volts. Understand this. This is what we have done here. This is what we have seen here. Okay. So whenever I'm having this kind of setup, I'm always sure that something is wrong here. Just let me correct it. This should be E. Okay, let's make sure about it. Okay, so when I am having this particular configuration, VBE always remains 0.7 volts. So that is as far as the common collector input characteristics is concerned. Okay, these are the output characteristics. When we say output characteristics, it means that it is output current versus output voltage, and we already have output current as IE, so it is IE versus VEC. This is, and what do you see here? These characteristics are virtually identical to common emitter output characteristics. They are virtually identical. So all the regions like active region, saturation region, and so on and so forth, all that is valid for this. So no need of talking about this in further details. All right. Okay. To end the basic concepts, we will just have a fast comparison of all the BJT configurations. Okay. How do we compare the configurations? Based on the input resistance, based on the output resistance, the voltage gain, the current gain, and the voltage gain primarily. This is just for your understanding. So when I talk about the characteristics as input resistance, for common base, we have seen that it is very low. It is of the order of 10 ohms. Input resistance is low. Just go back and corroborate with your notes if you have taken any. Common emitter, it is low, but it is in the order of kilo ohms, 1 kilo ohm, etc. Whereas in common collector, the input resistance is pretty high. Today's lecture, we have already seen that the input resistance is very high. So it is of the order of, these figures just are telling you what is the general order of values. Okay, low means what, high means what, okay, very low means what, that kind of thing which I want to prove, and that is the reason why I'm using specific values over here. It is not necessarily always true that it is going to be 10 ohms. It can be 20 ohms, it can be 15 ohms, depending on the transistor characteristics which we are going to see. Okay. So this is about the input resistance. What about the output resistance? The output resistance for common base is very high. We have already seen that. And what is the reason for that? We have already seen the output characteristics are actually the IE. IE is a straight line. Sorry, IC is a straight line. Okay, and it changes only with IE. So we have very high output resistance. If you look at the output characteristics, you will be able to understand this. For common emitter, it is high, but not that high, of the order of about 40 kilo ohms. Whereas for common collector, we have seen that it is pretty low. The output resistance or output impedance is very, very low. That is of the order of 50 ohms. Okay. Here in this case, the current was emitter current. The input current in case of common emitter is base current. Here also we have the base current. Output current was collector current. Here in this case it is again collector current, whereas here it is emitter current. Input voltage is applied between emitter base junction. In case of common emitter, input voltage is applied between the base emitter junction. In case of common collector, the input voltage is applied between base and collector. Output voltage is taken across collector base junction in common base configuration, collector emitter in case of common emitter configuration, emitter collector in case of common collector. Current amplification factor, we have seen it is called here as alpha, which is a ratio of IC by IE, and it is less than 1. We already know that. Okay. Whereas alpha is normally of the order of 0.95 to 0.995. Beta is the current amplification factor. So we have IC over IB. Okay, and that we have seen it is in the excess of, here you can see it is in the excess of 20 to 300. For power transistors, just make a note somewhere. For power transistors means the transistors which have larger collector currents and larger collector emitter voltages. Those are called as power transistors. So collector current will be in the range of amperes, 1 ampere, 2 ampere, 5 ampere, 10 amperes. In such situation, they are called as power transistors, and they have very low comparatively value of beta. Whereas those are called as a large signal transistors or power transistors. Whereas the transistors which have collector current in the range of milliamperes, they are called as small signal transistors, and they have a pretty large current gain. Same is the situation for common collector, because we have seen that they are very identical as far as the current gain is concerned. Voltage gain, we have a medium voltage gain. Here also common emitter, we have a medium voltage gain. But in common collector, the voltage gain is less than 1. We have already seen this also. What about the phase shift? There is no phase shift. Whereas we have seen here an example, there is a phase shift of 180 degrees. Whereas in common collector also there is no phase shift. This table is very important. I think you should copy this down or maybe make a note somewhere. This always is going to be helpful for you. Okay, so then you will ask me what are the applications of these configurations? Where are they used? Now, in most of the times, wherever you require low input impedance. Now, where would you require low input impedance? Specifically in case of the moving coil microphones. So if I want to amplify the signal coming out of a moving coil microphone, whose impedance itself is very small, I want to match the impedance over here, and so I can use common base amplifier over there, and it is called as a pre-amplifier. For those who are music fans, they will understand what is this preamp. Okay, so common base configuration is mostly used in preamps, and where you have interfacing with the moving coil microphones. At the same time, common base is also used for RF amplifiers, radio frequency amplifiers, very high frequency amplifiers. Okay, common emitter is mostly used for the voltage amplification in the audio frequency range. So if I want to amplify the signal coming out of the microphone, it is given to pre-amplifier, output of pre-amplifier I want to amplify, which is in millivolts. Maybe I want to amplify it to volts. I will use common emitter configuration. Okay, and common collector configuration is a very interesting thing where it is used for interfacing. So whenever you would like to interface, say for example a loudspeaker, if you want to interface, so the output stage will be always common collector configuration. Okay, so this is a comparison of the BJT configurations. All right, now for the remaining part of the lecture, let me see if we can introduce. Yes, I can. Okay, so I do have time for that. So the next part is the transistor H parameter model. Okay, so we'll just have a brief look at the H parameter model. Okay, any doubts, any questions so far?
No, sir.
Is it absolutely clear to all of you? Now, again, I'm telling you this, that if you just look at this, my presentations and my lectures, just like a movie, then it won't help you if you don't go back and revise whatever we have done in the lecture. It won't help you at all. These are the fundamental things. If you don't understand these things, if you don't digest these concepts, it is going to be very, very heavy for you to sail through in the entire program itself. I'm saying not only the course, I'm talking about the entire program, because all these things are the basic concepts which you'll be requiring for the future courses. Well, nothing to get afraid of. Once you start revising your concepts, it will be pretty easy for you. Okay, let us have a brief look at the transistor parameters, and after that tomorrow we will start with transistor biasing. So let me switch back to the node, OneNote. We'll start with a fresh page. Okay, and then we will start with the transistor H parameters. Now, as I have already told you that the transistors are non-linear devices, okay? Or let us say you cannot really analyze the behavior of the transistors in simple ways. So that is the reason why what we do is we introduce what is called as a hybrid model. Remember that if I want to simplify the analysis, I have four things with me. In fact, primitives which I called. So the primitives, what are the primitives? We have the current source, we have the voltage source, we have the resistors, we have the capacitors, and we have the inductors. Most of the times for the application, for the low frequency applications, we are not concerned with these parameters, with these, let us say, primitives. So if I am able to describe the transistor in terms of the primitives, for example, the current source, voltage source, and resistance, I will be in a position to easily apply our basic theorems and laws, specifically the KVL, the KCL, and analyze the circuit. And that is the reason why we describe the transistors in terms of its hybrid model. Now, how do we have this hybrid model? Let us say I have this transistor over here, which I will essentially call here as a black box. So this is your BJT. We have already seen this. So I can describe this as a two-port network. This is your input current I. This is your output current IO. We have already seen this. So this is VI and this is VO. Okay. So we already know that II is the input current, IO is the output current, VI is the input voltage, VO is the output voltage. Now we have this very important relations. Please concentrate on this. We can write VI as a function of F1, function F1 of two parameters. One is II and the other is VO. Similarly, I can write IO as a function of the same II and VO. Now you will ask me, how do I get this? Okay. So let me first write this completely. Concept you have till now. This is the crux of, the basic turning point. VI can get affected by this VO. Is the meaning of this? Yes. So VI is a function of input current and output voltage. Similarly, IO can get affected by this voltage as well as the input current. This is what you have to understand. Okay. Yes. Any doubts, any questions? Somebody wants to speak? Now I can write this in this form, Vi as, I'll call this factor as H11 into II plus H12 into VO. Similarly, I can write IO as H21 into II plus H22 into VO. These are very, very important and fundamental starting point equations. Why I have written H11, H12, H21 and H22? The reason for that is Vi is a function of II and VO. So there will be some constant here, some coefficient. So these H parameters are nothing but coefficients. Okay, H parameters. These are called as H parameters, and they are nothing but coefficients. That's all. Now
सर बीच में आपका आवाज चला जा रहा है सर.
Describe the behavior. If I am able to repeat that, if I am able to figure out, if I am able to find out H11, H12, H21 and H22, I can figure out everything about the network. Okay. Now I'll just drop the suffixes over here, change the suffixes over here in a peculiar way. Watch me. Di is equal to H. I'm going to call this as Hi because this is to the input side. Hii into II plus HR into VO and IO as HF into II plus HO into VO. So I have now converted, rather I have changed the suffixes from 11, 12. These are basically the ports. So if I call this as 1, 1 dash, 2, 2 dash as the port, you will understand that. Okay, this also gives a very interesting picture. What is that? The picture that we get is that H11 or Hi, which we are calling, which is actually H11. Now, if I want to find this out, what should I do? If I have got these equations, right? So what should I do? If I want to find out Hi or H11, what should I do? I should make VO 0. Agreed?
Yes, sir.
Okay, so if I make
Yes, sir.
If I make output 0, I can simply find this as Vi divided by II, where Vout is equal to 0. But what is Vout equal to 0? Means I am putting a short circuit here. Correct? Yes or no? Look at the units that the dimension that I want to get. It is a ratio of voltage to input voltage to input current. So can I write it simply as input resistance with a special case? What is that case condition? With output short circuited.
Short circuited.
All right, and it is in ohms. So I have got a very interesting way. I mean, this Hi deals with the input resistance, or Hi directly gives you the input resistance. Hi is nothing but the input resistance. And how do I show that input resistance here? By looking into this port. So if I have a source somewhere, what will the source see? It will see a resistance which is nothing but Hi or H11, which is nothing but the input resistance of the network. ठीक है ना? Let us continue with the other things also. What is H12? How do I get H12? H12 is called as HR here in this case. So this is H12. Now if I want to find out this, what should I do? If I want to find out this HR from this equation, what should I do?
Sir,
I should eliminate II.
II को 0 करना पड़ेगा.
II equal to 0 means what?
Open circuit, sir.
It is open circuit.
Input current 0.
Yes, input current 0 means open circuit. And this I will be able to get simply HR as VO divided by what? VI. Sorry, it's the other way around. Sorry.
VI upon VO.
So yeah, it is VI divided by VO.
A upon VO.
But what condition? II equal to 0. So I can call this. So what is this? This is the ratio of voltages. So it is unitless. This is unitless. And what does it tell you actually? It tells you that it is the fraction of output voltage which appears at the input when or with input open circuited. Very, very important. So this is again unitless. By the way, you ponder over the thing that why in the first place the part of output voltage gets reflected on the input side. Well, that is the characteristic of any network. So we can have a part of output being reflected at the input, and that part we are calling as this HR. Okay, we will continue now. What is this HF? It is H21. How do I find out? Similar way?
Sir, VO 0 कर देंगे.
Yes, VO को V output voltage को वापस 0 करना है. And what do I get?
I1 upon IO.
It will be
I naught upon I1.
I naught upon I1. But under the condition? And what does it
P equal to 0.
It is again a unitless quantity. If you remember, it is a ratio of two currents. It is unitless quantity. And what does it show you?
Sir, short circuited.
It is the forward
Short circuit.
current transfer ratio. With output short circuit.
With output short circuited.
Do you recognize this, by the way? We have already seen what is the ratio of output current to input current in case of common collector, common base, common emitter. In case of common base, this actually is nothing but alpha. In case of common collector and common emitter, this is nothing but beta. Please remember this. So we are going to correlate these things with the things that we have already seen. Okay, then what about H22, or it is actually HO? How do I find that out?
सर आई को 0 कर देंगे फिर से.
Yes, the same thing again. So then I'll get this as IO by VO when II is equal to 0. And what is the unit for this? What is the unit?
So your voice is lagging.
What is the unit?
Sir, Siemens.
Absolutely correct. This is nothing but the unit is Siemens. In older terminology, it was called as MHO. So this is nothing but output. Output resistance is called as output. Inverse of resistance is called as, or inverse of impedance is called as admittance. So I will use the word here, admittance. Okay, it is a reciprocal of impedance, but with input open circuited and capital S, Siemens is the unit. Okay, so are we through with the H parameters here?
Yes, sir.
All right, fine. So let it settle down for today. The remaining part I will talk about tomorrow. We'll see how these relate to different configurations. Okay. For the remaining part, I would like to get some feedback from you. Any doubts, any questions? Because normally we don't get time for interaction. We carry on with the lecture and very less time we get. So yes, I will start giving you the simulation exercises. My assignments are characterized by the work rather than writing it down like a clerk, copying down, show the explain how it works, and the such kinds of assignments I don't prefer. But you will have very interesting assignments like, why don't you simulate this particular circuit? Why don't you simulate this, that? So I'll just show you a couple of simulations, and then we'll expect you to carry out the same simulations at your own premises. So just let me fire up multisim. Okay, if there is any doubt, any question, please raise your doubts and questions.
Sir,
Okay,
could you explain the common collector current characteristic again?
Current characteristics. Which one? Input or output?
For input.
Input side. Input side. It is better if you simulate those and see. Okay. That is exactly what I'm trying to show you now. I know this question was going to be there, so it is better if I switch to multisim. Okay, are you able to see the multisim screen?
Yes, sir.
Yes, sir.
Okay, so let us start with a very interesting. How do you plot the characteristic of a simple PN junction diode? So I've got a lot of simulations here. So let me a very simple way. just put a current source of 1 microampere. Okay, use a voltage probe here. You can use the voltage probe from here, from this toolbar. Okay, so I'm just using a voltage probe here. Okay, in analysis, this is interesting. You have to go and select the DC sweep. You have to select the DC sweep. All right. Once you select the DC sweep, the source you can select as your current source, and the range that you can give, you can start with 0 amperes and stop at, let us not say 1 ampere, let us say 100 milliamperes. So it is 0.1 ampere. And the increment, be specific about this, should be 0.001. Okay. Click on this output, and here you are observing the probe, that is this voltage. This probe you are observing. What is our objective? Our objective is to run the simulation in such a way that the current flowing through the diode changes, and I'm just observing, I'm just measuring and plotting the voltage across the PN junction diode. That is the basic idea. Okay. Now if I run this simulation, you will see that you have a peculiar structure over peculiar characteristic or curve over here. The only thing is that it is a little bit, it is rotated. I cannot have the one which is like what we had already seen in the, but it's exactly the same. This is the voltage axis, this is the current axis. Normally we have the current axis vertical and the voltage axis horizontal, but doesn't matter. As you can see very clearly here, after a certain value, the voltage goes on, the current through the diode goes on increasing after the cut-in voltage. Now here you'll see some kind of a corner here, which we can do away with. You can have a very fine kind of, so if I just increase the resolution, that is increments, I'm just cutting down more increments, and now you'll see the exact thing. Okay, you can just have a cursor over here and just a grid over here. If you don't like the background, you can have this, and you can just measure the cut-in voltage. So you'll see that approximately at about 0.5 volts, this has started rising up. I mean, exactly at this point, nearly 0.6 volts. As I said, the cut-in voltage is 0.6 volts. So this is how you plot the diode characteristics. Is this clear to all of you?
Yes, sir.
Yes.
Okay, so this is going to be your very first assignment. I will post it on Edit. Next is, let us say, the common base characteristics. Okay, here also I am using NPN device. Again, what I am doing is I have two sources now, one current source and one voltage source. Now we are not interested in the output side, we are interested only in the input side. So exactly like the diode, I am just incrementing the value of this current source. Look at the direction of the current source, of the current basically. Again going into DC sweep, I am trying to find out for different values of BCE, for different values of BBC, we have shift in the characteristics, no? If you remember, that is because of the pulse width, because of the base width modulation, or also called as the early effect. So if I run this simulation, you'll see it is exactly like the diode. We have already seen this, but then for different values of the output, the base collector voltage, we have the different values of these curves. Okay, and you can see very clearly what happens here. All right, so this is the input characteristic of common base. We have already seen the characteristics in more details, so you just have to corroborate with whatever I have told you. What about the output characteristic? The same circuit. The only thing is that now I am See here what is happening. So actually this is going a bit negative, but we are normally used to having it starting from 0. So I'll just change the properties. Instead of I will start with 0. Okay, so this is how the transistor characteristics will look like. This also yeah, it is essential over here because we have already seen that the characteristics actually extend in this part of the region also, the second quadrant also. We have seen why this happens. So this is the common base output characteristics. Now there is some error here. Let me do away with this all, and then I can run this. Okay, so this is the bug in multisim, that it does not refresh the title. All right. Okay, I think we have run out of time. We'll start next time. Tomorrow we'll start with the output characteristic, input characteristics, like in how do you plot in multisim, and then we will continue with our H parameters. All right.
Okay, sir.
Okay. So I will sign off right now.
Thank you, sir.
Thank you. Thank you.
Thank you, sir.